Hello everyone, today we're going to start off physics with classical mechanics. So what is classical mechanics? We're basically just studying motion in a straight line today. Just an introduction to basic classical mechanics. And tomorrow we're going to dive deeper into motion in a plane and then rotational motion, work and energy, and more concepts to come. So, what is motion in a straight line? First, what we should know is that there is no absolute rest or motion. Motion is a combined property of object and observer. What does that mean? That means motion is relative. What does motion is relative mean? So let's say there was someone standing here and there is a train track. Well, it's not splitting him in half, but there is a train track right here and there is a train going on this track. Now let's say these are wheels. And there are two people inside this train. Say one is in purple and the other one is in red. So when you look at the red person from the eyes of the purple dude, what do you see? You see this dude is in rest. If he is looking at this dude, you can see that both of them are at rest. He thinks he's at rest and he thinks he's at rest. But when you observe it from the perspective of the green dude, both of them are in motion. That's what relative motion actually means. So there is no absolute rest or motion. Motion is a combined property of object and observer, which means motion depends on the observer as much as it does on the object. So we know some basic concepts already about motion and kinematics. What is that? We know that speed equals distance over time. And velocity equals displacement over time. And acceleration, so these are vector quantities, so I'm just going to get an arrow above it. Acceleration is equal to change in velocity over change in time. Or you could say final velocity minus initial velocity over change in time. So these are some stuff that we already know. And we're going to learn more about the equations of motion that we have already learned in lower grades. So you have three equations of motion. These are your three equations of motion. And we're going to learn more about these equations, and we're going to basically derive everything we've learned so far. So what we've learned so far is pretty clear. Acceleration is change in velocity over time. So if I gave you a velocity time graph, this is time, and this is velocity. So what would constant acceleration look like? Constant acceleration would look something like this. You can see that it's constantly accelerating. So the rate of change of acceleration is not changing. So it's constant. The rate of change of acceleration is not changing and it's constant. So this is known as constant acceleration, and therefore you can apply this formula. Acceleration equals final velocity minus initial velocity over change in time. And this arrow just means it's a vector quantity. What are vectors and scalars? Scalars are something that only have magnitude. Like, for example, if I said 4, the number 4 is a scalar quantity. Because what is it? 4, uh, like 4 meters to which direction? Like that. So if I gave you like the length. Let's say this was 5. If I give you the length of this line segment, that's just a scalar quantity. But let's say, what's a vector quantity? A vector quantity is something that has magnitude and direction. Like, let's say I was here, and there is a very heavy bag right here. Okay, and I was pushing this bag. So this is a vector quantity because we're pushing it to a direction. You can see that we're pushing it to this direction. So this push would be a vector quantity. Or you could say that we're applying pressure on the bag. So that's why we put an arrow above the acceleration line. Now we're going to talk a bit more about um non-continuous acceleration, or acceleration where it's not constant. Like, let's say your acceleration looks something like this. So your acceleration was initially slow, and then it slowly picked up some speed. And it goes super fast to where you can't even calculate it anymore. So what if your acceleration was like this? How do you calculate the acceleration? So there is no way to calculate this acceleration. If you want, you could draw a line right here where it intersects both of these points, and you could take the slope or gradient of this line. Like, this is delta y, and this would be delta x. And that's just your average acceleration. You could still use the acceleration formula, a equals v minus u over t. But what do we do to actually find the perfect, like, not even approximation? We're going to find the instantaneous rate of change. What do we do? So you may have or may have not learned derivatives yet. What is a derivative? A derivative is the slope of a tangent to a curve where the limit is approaching 0. So let's say I wanted to find the acceleration at this point. So then I would draw a tangent to this point like this, something like this, or a secant line. And as you can see, it's intersecting another point. Now you can see that this is change in x. This is change in x, and this is going to be change in y. And you can see here that I'm just going to write it down so we don't remember. Change in y, change in x. Now, how do we find change in y over change in x? That's just, change in y is just y2 minus y1. Or let's say there were two functions. This is going to give you an x, for which it's going to give you an output f of x. Or let's use the closer point for that. This would be x, and the output is f of x. And let's say you add some distance h. So this would be x plus h, and this point right here would be f of x plus h. Now, how do you find the gradient or rate of change of this line right here? To find the rate of change of this line, we're going to use the formula of a slope. What is delta y? Delta y is y2 minus y1. We're just final y minus initial y, which is f of x plus h minus f of x. And over delta x, because we're trying to find the slope of the line. And what is delta x? X plus h minus x. And these cancel out, giving us just h. Now, this is the slope of this whole line right here. But I want the slope only of this point. I only want the slope of this point. So what we're going to do is we're going to set limit of h approaches 0, which means it's constantly getting smaller. It's constantly getting smaller until it's at one point. And that point is x. So we're going to apply this limit. Limit of h approaches 0 of f of x plus h minus f of x over h. And this is your derivative. So how do you represent a derivative? This is dy over dx. So this is your dy over dx. What is dy over dx? So you know what delta y over delta x means. Delta y over delta x means change in y over change in x. So the same way, dy over dx means instantaneous change in y over instantaneous change in x. This is not the correct way to write it. So the correct way is just to write it down as a derivative, dy over dx. So what does derivatives even have to do with anything that we're doing? What does it have to do with what we're doing? I said, what if your acceleration is not a straight line? What if it's not constant? I said, what if it's curved like this? And I want to find the acceleration at an exact point. Now you see where I'm going with this. We're going to use derivatives to solve for the acceleration at one point. Now, how do we do this? Let's say I gave you your acceleration. So I told you, if you graph it like this, and this is x, and this is y, your derivative would be equal to dy over dx. But what if I made this velocity or time and velocity? What would this be? So your derivative here, or instantaneous rate of change of any point, is dv over dt. And this is your instantaneous acceleration at a point. So if you ever want to find acceleration at a point, you have to use acceleration equals dv over dt. You don't have to use the arrows, but I just prefer to use them because it shows that they're vector quantities with a direction. Now, what if they gave you acceleration and they want velocity? And they want you to find the velocity. Now, what if you multiply both sides by dt? Then you would get acceleration dt equals dv. Now, you integrate both sides. What is integration? Integration is just the opposite of a derivative. So, we're going to be going deeper into this in Calc 2 and Calc 1. So for now, just remember this. If you get anything, let's say the integral of dx, or the integral of dy, or the integral of du, then this is going to be x, and this is going to be y, and this is going to be u. Just remember that for now. So, what were we doing just now? We were solving this equation, differential equation. And this gives us v. This gives us v. This is v. So your instantaneous velocity, or at a point, if they give you the acceleration and they ask for the velocity, then your answer is going to be v equals the integral of a dt. This is your formula for velocity. And another thing we could do, I'm just going to plot down the formulas one by one because you need to remember these, and they are super important for physics. Acceleration equals dv over dt. Let me keep the arrows. Velocity equals the integral of acceleration dt. And now we're going to dive deeper into a few more, which we're going to derive by ourselves. So we know that so acceleration equals dv over dt. Now, if we draw a position time graph, what is a position time graph? This is your displacement, or this is your time, and this is your displacement. Not like our other graph where we had here time and here velocity. This is a velocity time graph. And this is a position time graph where we have time on the x-axis and displacement on the y-axis. So what would constant velocity look like on this graph? Constant velocity on this graph would look like this. Because you're traveling equal distance at equal time, at equal intervals of time. So that's just a position time graph. And we know acceleration equals dv over dt. But what if I said velocity, let me keep the arrows, velocity is also equal to, let's denote displacement as x here. Displacement here is x. So velocity equals dx over dt. And that's just common sense, because if acceleration equals dv over dt and velocity is change of position over time, then velocity is equal to dx over dt. So this is another one of your formulas. And if they ask you for your if they ask you for position and they give you velocity, then you're going to multiply both sides by dt. And here you can see v dt equals dx. And now x, and you integrate both sides, equals the integral of v vector dt. So this is another one of our formulas derived. Now, I said acceleration equals dv over dt. And I said velocity equals dx over dt. So why don't we submit this into the original equation, giving us acceleration equals d by dx of d, okay, so this is d by dt. I'm getting too used to math. Dx over dt. And now you can see this is a double derivative. And a double derivative is generally represented like this. Acceleration equals d squared x over dt squared. Which means you're just differentiating position 2 times. Okay? And there are some power rules. There are some rules in differentiation. D over dx of x power n equals nx power n minus 1. This is just one you need to remember. For now, we're not going too deep into calculus or derivatives or integrals. Nothing too much yet. So, what have we found out so far? What have we discovered so far? We've discovered that acceleration is actually equal to dv over dt. And we have discovered that velocity is equal to the integral of acceleration dt. And we have also, in fact, discovered that velocity is equal to dx over dt. And not only that, we have also discovered that x is equal to the integral of velocity dt. And another thing we've discovered is that acceleration is equal to d squared x over dt squared. So, this is some formulas that you need to remember. And another one is, let's say you had a number line. Okay, let's say you had a car. A car is moving. Okay, this is not a very good car. But let's say this was 4 seconds. And this was 5 seconds. And I asked you, how much distance did it travel in this interval of time? So, your formula for that would be S nth, where nth is your second term, and this is equal to u plus acceleration over 2 times 2n minus 1. So you just need to keep this in mind. Now we're going to think, and we're going to do some, uh, we're going to derive some formulas. So we know our equations of motion, right? How did they actually come? V equals u plus at, right? S equals ut plus half at squared. And what was the last one again? V squared minus u squared equals 2as. How did they actually? Why don't we start with V equals u plus at? Let's start with this one. So we know that acceleration equals dv over dt, right? And we know that adt is equal to dv. We multiply dt by both sides, and if we integrate both sides, there is going to be a definite integral, which you guys do not know yet, or you may, I don't know, but I haven't taught that yet. So I'm just going to do this step without any explanation, because you will understand it if you watch the future videos. And this one, you integrate it with bounds v to u dv. And a would be constant, so it comes out times t to 0 dt, and this is going to be limits of v to u. Now, acceleration of, so I told you when you get dt or something like that, that's just going to be t. But here we applied limits, t to 0. So what is a definite integral? I'm just going to give you a little example. Let's say you have some f of x, some function, dx. You're differentiating that function, and you have some limits b to a. Then, let's say after you solve this integral, you're going to get some other function, big f of x. Then you apply these limits b to a. And this is going to be f of b minus f of a. So we're going to use that here. This is going to be a times. So if we substitute t in t's place, that's just going to be t. Minus, if we substitute 0 in t's place, that's going to be 0. And this, if we substitute v in v's place, that's going to be v. And if we substitute u in v's place, that's going to be u. And this is acceleration times time equals v minus u. Now we add u to both sides, and you get v. Let me just fix this. Here. V equals u plus, this is actually a vector too, what am I doing? Plus acceleration times time. So, you see how we derive this formula? By using integration. Now let's try another one. What about s equals ut plus half at squared? So we know, so s equals ut plus half at squared. Now, we know that v equals dx over dt. Now, we know, so if we multiply dt on both sides, we're going to get v dt. Let me just draw the arrows, not there, equals dx times dt. Or actually, here, we multiply dt on both sides, so that's just dx. And now we integrate both sides, and actually, here we know that v equals u plus at, so we're going to substitute that here. dt equals dx. Now we're going to integrate both sides. And this is going to be final x minus initial x dx. Now, when we integrate both sides, this integral will split into two because there is a law in integration. The integral of f of x plus or minus g of x whole dx equals integral of f of x plus or minus integral of g of x. So we're going to use that here. This is going to be t to 0 u dt plus t to 0 at dt equals x final minus x initial, and that's dx. So we're just going to get x with intervals x final, x initial, or bounds, I should say. So when we do this, we get ut plus, so a comes out because it's constant, and this is t to 0, and this is t to 0. You get t dt equals, so if you apply these limits, you get x final minus x initial. And actually, there is another law for integration. That's why I should have taught integration and differentiation first. This is going to be x power n plus 1 over n plus 1. So, and there is a constant of integration, but we're not going to get into that now. So let's use that. So if we substitute t in ut's place, that would just be ut. And if we substitute 0, that will just be 0. So no need to do any of this. This is just going to be ut. And here, this is going to be t squared over 2. Why? Because I said x power n dx divided is equal to x power n plus 1 over n plus 1. So ut plus a times t squared over 2 with intervals t to 0 equals x final minus x initial. And this is ut plus, if we substitute t, we're going to get the same exact thing. So this is a t squared over 2 equals, and x final minus x initial is just another way to say distance, so we're going to represent that as s. So you get s equals ut plus at squared by 2, or you could say s equals ut plus half at squared. So this is how you get your second equation of motion, s equals ut plus half at squared. Now we're going to go to the third one. V squared minus u squared equals 2as, and then we're going to wrap this up with a few questions, just a few. Now, we know that acceleration equals dv over dt, and actually these problems we're deriving right now, these equations, they're actually very important and are asked in a lot of exams. So we multiply both sides, or the numerator and the denominator, by dx. And giving that, this would give us a ds equals v dv. Now we integrate both sides. This is final. Or instead of x here, we're just going to keep s because I already wrote s. So s and x mean the same thing. So this is going to be final distance, initial distance, and ADS. And this is going to be equal to V to U, V dV. Now, A comes out because it's constant. ds equals integral of V to U, V dV. And this is going to, this right hand side, let's just simplify that after. This left hand side is going to give us V squared over 2, as I said, with intervals. Let's draw that cleanly. With intervals, V to U. And this left-hand side, what was here? This was ds, I think. So this is going to give us as, but s has intervals s final, s initial. And if we substitute this here, v instead of v's place, we get v squared over 2. And if we substitute 2 in v's place, we get u squared over 2. And this is s final minus s initial, just substituting in their place. And v squared minus u squared over 2 because we're just combining the numerator because the denominators are the same. And this is just s because that's just distance. So v squared minus u squared over 2 equals as. V squared minus u squared equals 2as. So this is your third equation of motion, and we've derived it. And you need to keep this in mind and learn integration quickly so you understand most of this. Now we're going to do some problems. What if I said, find the velocity, if, find velocity at, let's say, 2 seconds, if, let's say, time or position, if position is given by position is given by t to the power of t. Now this is a complex one because you guys don't know differentiation yet, so I'm just going to solve it with you. Or I'll give you a simpler one because you guys don't know differentiation yet. Plus 8. Yeah, that looks good. So find velocity at 2 seconds if position is given by t cubed minus 3t squared minus 2t plus 8. So how do we do this? We know velocity equals dx over dt. And x equals t cubed minus 3t squared minus 2t plus 8. Why? Because that's your position. Now, why don't we substitute this into the equation? V equals d by dt of this whole thing. T cubed minus 3t squared minus 2t plus 8. And actually, derivatives break with plus or minus 2. So velocity equals d by dt of t cubed minus d by dt of 3t squared minus d by dt of 2t plus d8 over dt, or you could just write it d by dt of 8. So let's use our power rule, nx power n minus 1. So this is 3t squared minus 6t minus 2. And the derivative of any constant is actually 0 because there is no rate of change in a constant. So we're just going to leave it like this. And they said, find the velocity at 2 seconds. So what's the next step here? We need to substitute 2 in place of t. Because t is 2 seconds. Time is 2 seconds. 3 times 2 squared minus 6 times 2 minus 2. So this is 3 times 4, 12 minus 12 minus 2. So time can be negative, but velocity is negative 2 meters per second. Which means if someone is moving this direction, they're going in this direction. That doesn't mean like velocity can't be negative. Velocity is a vector quantity, which means it can be negative. Now let's try another one. Let's say I give you the position and I ask you to find velocity. So, okay, I give you the velocity and I ask you to find the position. Let's say velocity is given by, what's an easy one? um, let's say sine squared t cosine of t, and yeah, so find the position. So we know velocity equals dx over dt. Now if we multiply dt on both sides, we get v vector dt equals dx. And if we integrate both sides, we get, that was not a good integral sign, v dt equals integral of dx, which is just x. So we're just going to write x equals x. So let's use this formula. Velocity is given by sine squared t dt. And so this is actually position function. Why? Because there is no numerical value for it. So let's substitute sine squared t cosine of t, cosine of t dt in place of velocity equals x. So to solve this, you actually need to use u substitution, which you guys don't know yet. U equals sine t du over dt. We're just going to differentiate both sides, which gives you cosine of t. And if you multiply dt on both sides, you're going to get cosine of t dt. Now we're going to substitute this here. If u equals sine of t, u squared equals sine squared of t. So let's substitute this here. This would be u squared, and du is cosine of t dt. So u squared du. And I told you x power n integral dx equals x power n plus 1 divided by n plus 1. So u squared du is u to the power of 2 plus 1 over 2 plus 1, which is u cubed over 3. Now let's substitute, what is u? Sine cubed. Sine cubed of t over 3. And let's say they gave you at like some pi, find the position at, or let's just, yeah, position function, okay? So your position function is 1 over 3 times sine cubed t. So these were just some basic problems on motion in a straight line. Tomorrow we're going to start the real deal: projectile motion, trajectory, range of projectiles, maximum height, time of flight, time of descent, everything that you've learned, but a little bit deeper, I guess, with calculus. So make sure to like, subscribe, hit that notification bell if you like the lecture, and I'll see you in the next video.